Okay, we will start the lecture today. We will do 2.7 and then 3.2 and then 3.1. So today we will do 2.7, 3.2, and 3.1. Now, before I actually really start, I would like for you to start watching my last semester's lecture video from YouTube. Let me share with you what it looks like. So you go to YouTube, you type Arjuno, and click Thomas Arjuno. You can subscribe if I were you to make it easier for you, and then go to playlist, and then go to Math 2 SMC Precalculus. Now this is your class. This is summer 20 Math 2 SMC Precalculus. Okay. Now, but yours will be I want you to also take a look on the one from spring. Now, the way I set it up, the way I set up the lecture video, we will, from last semester, this is from last semester, and last semester we moved to remote teaching when I finished 2.7 at school. Okay, so what happened then with them? What happened then with them? I start 3.1 remote teaching. Okay, now the thing is, your class here is a summer and it's only 6 weeks. Every day we meet for pretty much 3 hours, right? Now with them, we met for 2.5 hours. So their one class is almost equivalent to our one class. But the thing with them is it's twice a week class, 2.5 hours. So they have more time to study. Okay. While with you, it's basically every day the same similar lesson, a bit more. So what happened is you will have less time to study actually compared to them, less time to study at home, even though the amount of material will be covered, should be the same. So yes, like what I said on at the beginning of this class, that the first day of this class will be fast, very fast. Now to help you, then I would like you to actually have access to these videos, okay? This playlist here. Okay, so now what happened is then the following. Today, after you do the suggested homework from 2.7 and 3.1 and 3.2, maybe you do the suggested homework from 2.7 first, okay, and then you watch this lecture video 3.1, 3.2 again, okay, and then do your suggested homework. Or if you are okay, you can just watch do the suggested homework. I strongly suggest you to start watching ahead of my class 3.3 and 3.4. So what I will do tomorrow will be 3.3 and 3.4, maybe a bit of 3.5. Okay, and then on Monday I will do 3.5 with 3.6, maybe with 4.1, and so on and so forth. So having this lecture video ahead of you, you watch that first before you come to my class, will make our class actually go faster. And we will use the extra time, because we can get faster, we'll use the extra time to do more problems. Okay, so instead of covering the same material on YouTube, okay, I prefer to actually cover more examples, problems from the book. Okay, I hope, so I actually don't need to do lecture video for 3.1, 3.2. You can just watch this. Okay, yeah, you can just watch this. Now, then I want you to use this time, especially during the weekend later on, you watch ahead, okay, such that when we get to chapter 3.5 and chapter 4, I can assume that you watched the lecture video already. Okay, now let me go back to our class. this thing does not show up. Okay, so what is 2.7? 2.7 is on operation of functions, operation on functions. Yeah, this operation on functions still not in our my other lecture videos, my lecture video on YouTube. It's not there yet. So what is operation of functions? We will separate this into two big portions. The first one is the algebra part, the plus, minus, multiply, divide functions, and domain. And the second part is on composition of function. And domain. Okay, now let's do the first part. The add, subtract, multiply, divide functions. Definition. Definitions. Let fx and gx be functions, actually any function. Okay. Then notation, f plus g of x is equal to fx plus gx. F minus g of x is actually fx plus minus gx. Fg of x means fx times gx. And f over g of x means f over fx over gx. So it's a instinctive definition. Okay, now the domain for the sum, difference, and product is the domain of f. Let me use this notation. Intersect the domain of g. While the domain here for the quotient is still the same, the domain of f intersect the domain of g, with additional situation that the g cannot be zero. Gx cannot be zero. Yeah, otherwise the denominator becomes zero. Okay, for example, example one, let's say fx equals to, the square root of x squared minus 3x minus 4, and gx equals to what is good? Gx equals to 3x minus 2. Let's say we have that situation. Then part A Find what is f plus g. What is f plus g at, let's see, good, at 4. Part B, what is f minus g at 4? And part C, f times g at 4. And part D, f over g at 4. Now, the definition for the one we have up there, each one of these require us to know what are f4 and g4. Okay, so let's compute that first. f4 is square root of 4 squared minus 3 times 4 minus 4. That's square root of 16 minus 12 minus 4. Oh, that's square root of 0, okay, which is 0. While g4 is 3 times 4 minus 2. That's equals to 10. Okay, so if we have specific number, we can add them one by one. f4 plus g4. That's 0 plus 10. That's equals to 10. F minus g at 4 is f4 minus g4. That's 0 minus 10. That's negative 10. Fg at 4 is f4 times g4. That is 0 times 10. That's 0. And f over g at 4 is f4 divided by g4. That's 0 over 10. That's still 0. Now, but this question A, B, C, D here are such an easy question that it's so easy that I don't think I will ever ask you. If I ask you, that would be bonus. Consider that bonus question. You have covered this algebra of function, add, subtract, multiply, divide, and even composition of function in your intermediate algebra. Okay, so my emphasis will not be what is f plus g at 4, what is f times g at 4. No, no, no. The further emphasis will be starting from what will, for example, f plus g of x. So instead of requiring that to be computed at 4 or any specific number, we deal with this as the sum of two functions. So these two functions, when you add them, it becomes this guy plus 3x minus 2. Okay. Now then part f, let's say if I have f times g of x, well, that the one above is actually fx plus gx, right? Now the one here, part f, it's fx times gx, which basically means the square root of x squared minus 3x minus 4 times 3x minus 2, which we usually write radicals after the ones without radicals. So it is a custom that we write this first multiplied by the square root something. Okay. Now, and then part G, for example, what is f over g of x? That is fx over gx. And even this, I believe, when you see this, you find it to be super easy, right? Now the discussion will go further, in fact, into the domain. Okay, so let me continue. Suppose I want to find the domain. G, and then now let me go to H here, part H. Find the domain of f plus g of x, which we know will be the same to the domain of f minus g of x, and we know that will be the same to the domain of f g of x, which if you observe the domain of the new functions after you add or you multiply or subtract should be those numbers that can be plugged into this function, the first function, and the second function. In other words, it has to be the intersection of those two functions that build this new function. Okay, so the domain will be the set of all x where x squared minus 3x minus 4 is non-negative. Okay, intersect with the domain of gx. Oh, that's a linear function, so that's a all real number, right? But it has to satisfy both. So you will see that the domain will later on restrict it to the domain of f only. Okay, now then, how do we solve that? We will solve it by x squared minus 3x to be greater equals to 0, and then you solve it using the 3 steps. Okay, step 1, critical number. Step 2, sign graph. Step 3, solution. Right? Okay, you will do that procedure, please. Okay, you will see the critical numbers are 4 and negative 1. Okay, you do the sign graph, you put the details yourself, okay? And you will see the solution will be negative infinity up to negative 1 inclusive union from 4 to infinity. Okay, now then how about part J or I, I'm sorry, part I. How about the domain of f over g of x? Then the domain here will be the same with this domain, will be the same with that domain, with extra requirement, and gx cannot be 0. Okay, now gx is 3x minus 2 cannot be 0, so x cannot be 2/3. Okay, now notice that this 2/3 happens to be not in the domain of the function fx anyway. So for fx is here, right? Okay, while for the second requirement, this is the domain. This is the domain of fx. Okay, the domain of gx is all real number. The domain of gx is all real number. Let's use this. Okay, and then gx cannot be 0 is everything except 2/3. So everything is okay except the 2/3. So you see that in this question, it happens that this 2/3 is not even in the first one. So the intersection of the first two, is the same to the yellow one, right? Now, the intersection of all these three here is still the same to the yellow one. So, the domain of f over g of x is the same to, happens to be the same to what we had. Because the number we actually need to exclude, 2/3, already excluded at the beginning. Okay, that's for this example one. I basically cover, using this one example, I cover half of this section. Now let's do problems from our textbook. Let's do problem from our textbook. Let's see, for example, number 8. Number 8, we have let fx equals to x over x minus 2 and gx be 7x over x plus 4. Okay, let me modify this question a little bit. Let me change this 7x here. So I modified that. I will make it 7 plus x. Okay, I will make it 7 plus x. Okay, I do a little modification. Otherwise, the question becomes not so interesting. Now then, the questions are part A. What are f plus g of x, f minus g of x, f times g of x, and f over g of x. Now, if I work it out, this will be the fx plus gx. Right? Now, sometimes you need to simplify that further, but here they just want you to add it, and I will just write it down. Okay, second, what if we subtract? That's what it looks like. What happens if we multiply? Then there will be x over x plus x minus 2 times 7 plus x over x plus 4. And finally, what if we divide? Then it will be x over x minus 2 divided by 7 plus x over x plus 4. Now that's if I just add, subtract, multiply, divide without simplifying them. Now, what if I need you to simplify? Let's say I say find this and simplify. Then when I simplify, I do the LCD for here, right? For example, this is x times x plus 4. This is x minus 2 times x plus 4. We have learned this in chapter 1. This is 7 plus x times x plus x minus 2. This is x minus 2, x plus 4. And then the reason we have LCD so that we can put them together under one fraction. So this is x minus 2, x plus 4. And up here we get x squared plus 4x. Okay, plus x squared. I will FOIL and distribute at the same time. And x squared plus 5x minus 14, which if I combine, I get 2x squared plus 9x minus 14 over x minus 2, x plus 4. That's if I simplify. Okay, the subtraction one pretty much the same. Just very careful that the subtraction here, you need to be careful because then you need to distribute the negative instead. Okay, I think somewhere in between here, if I skip that one little step, I will get x squared plus 4x minus x squared minus 5x plus 14 over x minus 2, x plus 4. Okay, what if I multiply? Well, just like before, we multiply as usual. The top with the top, the bottom with the bottom, and I will just leave them factorized. When we define rational functions, then we multiply by the reciprocal. X plus 7, and then multiply as usual. I get x times x plus 4 over x minus 2, x plus 4. Okay, now that's for part A. Now part B, how about the domain? The domain of the sum f plus g of x is equal to the domain of the subtraction of these two functions, and that those two are equal to the domain of the product of those two functions. And we can actually just do it visually. All these are equal to, we can just do it visually. Notice that the domain of fx will be all real number except 2. And the domain for gx is all real number except negative 4. So I will just write it this way. This is all real number except 2 and negative 4. Okay. Now, if you try to write it using interval notation, then you need to, you see that you need to avoid negative 4 and you need to avoid 2. Okay. I prefer you to write it this way, all real number cut off the set of 2 and negative 4. But if you want to use the long interval notation, that's also fine. Negative infinity up to negative 4, union negative 4 to 2, union to infinity. Okay, so you can use either one, either this one, or you can also use this one here. I prefer the first one. Now, the thing is, what happened with the domain of the quotient? The domain of the quotient is the same to the domain of the product, sum, or difference. It will be the same to these. Okay, the same to that, but with extra requirement. The extra requirement is that, and let me use intersection. The requirement is that they intersect all those x where the gx is not 0. Okay, but gx equals to 0 if 7 plus x over x plus 4 is not 0. A fraction is not 0 if the denominator, if the numerator is not 0. You can just multiply by the LCD here. So then you see x cannot be negative 7. Okay, so if I carry this on, then this will be all real numbers except 2, negative 4, negative 7. Okay, that's the domain of those. Actually, in your tests, I think in your test, or you will see later on in future tests, you have this kind of question. For example, find the domain of call that a new function hx equals to the square root of x squared minus 4 over x plus 3. Now, you see that this function is actually the quotient of two smaller functions. The first one is the square root, which means x squared minus 4 has to be greater or equals to 0, and at the same time, x plus 3 cannot be 0. Right? There are two requirements here. The second requirement is actually easy. If x plus 3 cannot be 0, then x cannot be negative 3. Okay, that one is easy. Then how about the first one, that x squared minus 4 cannot be 0? Hey, by the way, in my test, you need to show work. Yesterday, I looked at one student who actually turned in the test at 12:20 something. So that person only took 1.5, at most 1.5 hours. No, it's less than 1.5 hours to do my test. But that person didn't show enough work though. Okay, if that person is here or have listening to this lecture, to the video, I need you to be aware that I focus more on your work than your final answer. Okay, yeah, I focus more on your work than your final answer. I need to see the details, how you get those answers. Okay, some little steps I don't mind, like for this one here. Okay, I don't mind, but for this guy here, you need to show me work. Okay, you need to show me the work, and the work were. Let me continue using red. Step 1 is the critical number, and I want you to write it down, 1 critical number. But Thomas, I look at that, I know the answer. Trust me, if I can use that argument, okay, you can see that. You don't need me to explain that. Imagine if I use that thing. That's quite offensive for you, right? Okay, so while I explain it in that kind of details, I expect the same thing from you. That's why I show you this thing. Okay, I'm not giving you, try to make you understand, while when you give me your quiz or your test, you don't try to make me understand. You need to, okay? So the sign graph is this, and then the x-intercept was negative. I mean, the y-intercept is negative in this case, so it's negative, positive here, positive here. So I will get the domain for the square root is negative infinity up to negative 2 union 2 to infinity. However, so the overall domain of f hx will be this set here, and at the same time x cannot be negative 3. Now, put things together, then you will see. Let me draw it first. To the left of negative 2, to the right of 2, but at the same time it cannot be negative 3. Okay, so the domain will be negative infinity up to negative 3 union negative 3 up to negative 2 inclusive union from 2 to infinity. Okay, now that's for this first part, not too hard. The first part is not too hard. The slightly harder one, which is still not hard, is the second part. The second part of this section is on composition of function. Definition. The notation f compose G, it's an open circle in the middle. Open, small circle in midline. So let's say these are the lines for your paper, right? Okay, now the composition is actually put in the middle. Not above like a degree notation, no, it's not. No, not degree notation. Not below 2 as if it is a decimal point, like that the position of decimal point is not. Okay, it's a middle line. Now F compose G of X, that's how we read it. F compose G of X actually means the F of G of X. Okay, so it actually means the following. F compose G of X means that the X goes to G first, and then whatever the GX, the output of that GX becomes the input of that F. Okay, as if X go to a machine G, the output is GX. Now, then you plug that into machine F, the output is F of GX. Okay, that's what it means. Now, that's what composition function. Now, the way you read it, I'm sorry, my son is next to me. Yeah. The way you read it is X goes to G, and then whatever the outcome, you put it into the F. That's what it means. Okay, now then the domain of the composition of function is the domain of the resulting function Basically, composition of two functions give you a new function. Composition of two functions give you a new function. Now, what is the domain of that new function? Whatever that is, intersect with the domain of the GX. Okay. Basically, we are saying the following. For this composition of function to have a real outcome, the outcome has, if you want it to be a real number, then you need to get the X in the domain of G first. That's the first thing. Okay, that's the first thing. If that's not even the domain of the first machine, then there's no output here, right? Now, if there's no output to be the input for the next machine, then there's no output in the second machine because it's not even having an output in the first machine. Now, that's the idea. Okay, that's the idea. Now, let's say we take a look on the easy one, number 22. Part A, the functions are the following. Let fx equals to, let fx equals to square root of x minus 15 and gx be x squared plus 2x. And part A, find f compose g of x and its domain. Solution. F compose g of x is equals to the f of g of x, which is f of x squared plus 2x. So the input for my f right now, instead of x, my input now is that. Okay, so f blah is square root of blah minus 15. Okay, the square root of blah minus 15. Now, what is the domain of this function? The domain of this f compose g of x is the domain of the resulting function. So x squared plus 2x minus 15 should be greater than 0, greater or equal to 0. Now intersect the domain of gx. But gx is a polynomial such that the domain is a real number. Because gx is a polynomial. Yeah, if you have polynomial function, linear function, quadratic function, cube, polynomial, then the domain is all real numbers. Our issue is here. It's nonlinear inequality, and every time you need to solve nonlinear inequality, you need to do the 3 steps. First one, critical numbers. Okay, you will see the critical numbers are -5 and 3. But you need to show that, okay? You need to show that. Okay, and then second, you do the sign graph. You will find that when x equals to 0, that's -15, multiplicity of 1, multiplicity of 1. And then solution will be -infinity up to -5, inclusive union 3 to infinity. Okay, now, and together with this, you intersect with all real numbers. Okay, so the domain of this function is just the same to the domain of that radical. That's for f compose g. Now, part B, we will find that g compose f of x and its domain. So, solution, g compose f of x is g of fx. That's the g of square root of x minus 15. Now, g blah is blah squared plus 2 blah. G blah is blah squared plus 2 blah. Okay, so the blah squared will be blah squared plus 2 blah. This gives us x minus 15 because the square root cancel with the square, but the second part here is still the same. Now from here we see that the domain of G compose f of x is, we are okay with this, right? But the second part of the resulting functions requires that the x has to be, x minus 15 has to be non-negative. Okay. Now, and at the same time, you need to intersect with the domain of the incoming function, the domain of fx. Now, the domain of fx, let me do this one first. This is at least 15. Right? It turns out the domain of fx also the same, at least 15. So the intersection will be the same from 15 to infinity. Now the following is, in my opinion, a very good question. Number 26. Number 26. We have let fx equals to square root of 3 minus x. So the domain of f has to be less than 3, huh? 3 minus x less than equals, oh, sorry, greater equals to 0. So 3 is greater equals to x. So from negative infinity up to 3. And for gx, we have square root of x plus 2, whose domain of g is negative 2 up to infinity. Okay, now suppose, for example, the question is, I ask, what is the domain of f plus g of x? And it has to be the intersection between less than equals to 3 and greater equals to negative 2. Right? If you visually looking at that, sketch that, less than 3 means everything here. And greater equals to negative 2, everything here. Now, the one double shaded tells us what they have in common, which is from negative 2 up to 3. Now, how about f compose g of x? That's f of gx, which is f of square root of x plus 2, which is square root of, which is square root of 3 minus x plus 2. The square root of x plus 2. That is 3 minus square root of x plus 2. How about the domain? How about the domain of f compose g of x? Of course, from here, we see that first, x plus 2 has to be greater equals to 0, right? That's basically the domain of Gx. Okay, so we know that it has to be greater equals to -2, but we intersect that with all those x where 3 minus square root of x plus 2 greater equals to 0. Basically, I'm saying that this guy here has to be positive. Okay, now let's find that one. So this is 3 minus square root of x plus 2 greater equals to 0. So 3 is greater equals to square root of x plus 2. You square both sides, right? So 9 is greater equals to x plus 2. Okay, so x is less than equals to 7. So this means that from negative infinity up to 7. Now put these two together, this guy with this guy together. Give us the domain from -2 to 7. Now, I would like you to try part C. How about find out G compose F of X, find that, and its domain. Okay, together with your break, 1, 2, we come back at 12, 12:18. So I'm sorry, I forgot to unmute it. Oh, okay. Well, anyway, I hope my writing is clear. The last example for this section, the one that I do quite common in my test, similar, is when both functions are rational functions. So fx, let's say, is x plus 2 over x minus 1. And then gx is x minus 5 over x plus 4. Let me do a little modification. This could be too easy. So I will I put a 2 here and then 3 here. Okay, I do that modification. And then let's say we are interested in finding the find f compose G and its domain. So solution, f compose G of x is f oops, of gx. So that's f of 2x minus 5 over 3x plus 4. Again, I do modification. Okay, I do some modification. Now f blah is blah plus 2 over blah minus 1. Now I will simplify this. I will multiply by the LCD, 3x plus 4. Okay, but this also means that 3x plus 4 cannot be 0, right? Which is actually the domain of the incoming. That's the domain of the incoming function, the gx. The domain of gx is all real number except when 3x plus 4 equals to 0. Okay, so that's why it's actually okay for us to multiply by 3x plus 4 on the top and the bottom, because 3x plus 4 cannot be the domain of the function anyway. Okay. Now, if I do so, then on the top left, it will be the 3x plus 4 cancel. I get 2x minus 5. On the top right, I will have 2 times 3x plus 4. Bottom left, I get 2x minus 5 minus 1 times that. Fast forward. You need to show that though. I will just use dot 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 here, but fast forward, I will get 8x plus 3 over negative x minus 9. So what happened to the domain? The domain is all real numbers except, notice that you need to avoid this to be 0, right? You need to avoid that to be 0. Negative x minus 9 equals to, not equals to 0. Negative x equals to 9. X not equals to negative 9. So I need to avoid negative 9. And I also need to avoid 3x plus 4 being 0. Okay, so this is from the yellow one, and this is from the blue part. Okay, now suggested homework from here. From 2.7, that will be from, let's say, from number 3 to number 33. I think that's good enough. Number 3 to number 33 with the odd ones. Now, I expect you to study. Outside of this lecture, I do expect you to study approximately 6 hours outside of class time. So between today and tomorrow, please set aside 6 hours to study. Now, if you are fast and you have some confidence, it may be less. But that's what I recommend to every student taking the class, because the way our classes actually designed is the following. When you hear the term, basically the idea is this: for every in 1 hour, every in class hour, we need to spend 2 off class hours. That's the quote unquote the rule. Okay, that's quote unquote the rule. Now, so this class meets for 3 hours approximately. Let's say 2.5. Let's say 2.5 hours minus those breaks, right? It means outside of class between today and tomorrow, I do expect you to study for 5 hours. Now, please, and if you are someone whose foundation is weak, you may need to take more. Okay, but I do not expect anybody to say, Thomas, you give too much homework. And then when I ask how much time you actually spend to do your homework, I spend 2 hours to do my homework. Dude, it's supposed to be 5 hours. Okay, if you spend more than 5 hours, then you need to speed up. Okay, if in fact you need to pay attention to your speed all the time, right? But it's not about how many hours you spend. It's about what you actually do. Okay, in the end, it's about the result, and it's not the effort. Okay. People, when they look at your diploma later on, they did not ask you how long it took you to finish your degree. What they care is you finish the degree. Okay? What they care is you have your diploma. So you don't expect to apply for a job saying that, you know what, I should be a doctor because I already been in the medical school for 15 years, you know, but did you get your diploma? Well, I don't get my diploma, but I already studied that law. Well, it doesn't matter, right? You need to have your degree to apply for that kind of job. You cannot say you studied so much time, so long, and therefore you have the right to be a doctor. No, it doesn't work that way. I mean, it's not only that it doesn't work that way, however you try to fight it. Let me tell you, if you have that kind of doctor, will you let yourself be diagnosed with that person? Trust me, no. Not me, not a lot of people. If that's you, then go ahead, you do it. But that's not what I want my student to be, okay? I want my student, when they pass this class, they have all the foundation necessary to be successful in Calculus 1. And one of them is that you have enough time, right? You are fast enough to solve problems, okay? Yeah, so, but of course you also need to have the discipline to study. I will continue. That's the suggested homework. Let me circle it first. This is the suggested homework. Okay, and I would like you to, of course, do that. Next thing I will do is on division. I purposely set this division topic aside because this will be a big issue for us in this course, at least for the next 2 weeks. At least for the next 2 weeks. let's say 1 week minimum, maybe up to 2 weeks. Definitely up to your test 2. Okay, I wonder when's your test 2. Let me see the syllabus. Your test 2 is on the 17th. So today is the 8th. Yeah, 17 on the 17th. Oh, next Friday. So your next test is next Friday. Yeah, your next test is next Friday. Okay, now in this division topic, I will show you 2 types of division. The first one is long division. 2 methods. Long division, and this one always work, but slow compared to the second method is called synthetic division. That's fast, but only when the divisor is in x minus c form. Okay, long division first. I think I will give you 2 or 3 examples from this long division. I need you to be very good with that. Maybe two examples. Yeah, because if you have hard time in understanding this, you may go to YouTube and then search for long division. Okay. Yeah. Suppose long division. What we are going to do here is to divide a polynomial by polynomial by a polynomial. Note that these polynomials should be in descending order. Should be in descending order with placeholder in place if necessary. Placeholder in place if needed. So suppose for example, I have x squared, no, actually x to the third minus 16 over x squared minus 2x plus 3. I make up numbers. Yeah, suppose I have this. Now, what I meant by descending order is your polynomial needs to start from the highest exponent and one step at a time going to the smaller exponent. Degree of 2, and then degree of 1, and then degree of 0. Okay, so the degree has to go down one by one. Now, when I plug that into the long division, Okay, I start with x cubed, but degree of 2 is not there, so I will put in 0x squared plus 0x to the 1 minus 16. Now, what I meant by placeholder are these two here. These are the placeholder. Okay, so it has to be in descending order and placeholder in place when if it is needed. So x squared minus 2x plus 3 is the divisor. So it is outside. Okay, the numerator will go inside the house. Now then we will start. We will start. X squared times what? X squared times what? Give me x cubed. I need x, right, to make it x cubed. Okay, so I will put that x here according to the place value. I will put that x here. Now distribute that x with the whole polynomial here. So distribute that x with the whole polynomial. Give you this here. That will be x cubed minus 2x squared plus 3x. Now then we subtract. When we subtract, of course, we want this part here to cancel. That's why I multiply by x, so that the x cubed match with the x cubed and they cancel. Okay, now that's what you expect though. But then when this cancels here, when this guy cancels here, be careful with this, because what we have there is actually 0 minus negative 2. Okay, so that's 2x squared. Okay, and while this one here is 0 minus 3, that's negative 3x. We are not adding this. We are not adding this. We are subtracting. Keep this in mind. We are subtracting. We are subtracting. Okay, we are subtracting. And then the one that has nothing there, I will just copy that down. And I will do the process again. I will do the procedure again. Okay, yeah. Then the procedure will be x squared times what? Give me 2x squared times 2. So I will put plus 2 here and then distribute that polynomial by 2. That will give me 2x squared minus 4x plus 6. Which, when I subtract, of course, we expect the 2x squared cancel. But what happened with negative 3x and negative 4x? Well, that's negative 3 minus negative 4 give you positive 1. So this will be positive 1x. Okay, don't forget we are subtracting here. Okay, we are subtracting. And then negative 16 minus 6, that's negative 22. Minus 22. Now, once your degree now less than the divisor, this is degree of 1 here, but the divisor is degree of 2, then we know we can stop. Okay, so the solution is, so x cubed minus 16 divided by x squared minus 2x plus 3 is equal to x plus 2 plus whatever the remainder divided by x squared minus 2x plus 3. Okay, that's the final answer. Now, what I did here is very, very similar to dividing integers. Let's say if I have, let's say if I have 23 over 7. 7 goes to 23 three times, right? Okay, the remainder is 2 divided by 7. If I do the long division, that's 23 divided by 7. That's 3 times here for 21. The remainder is 2. Therefore, I write that 2 over 7. Okay, so that's what it mimics. Mimicking, is it right? Mimicking what we did in converting improper fractions to mixed number. So that's basically what we did there. And remember, this is subtraction also, right? This subtraction. Okay, now that's one example. Let's see another example. Let's see another example, and maybe I would like you to do this. You try this. For example, suppose we have x minus 3x squared plus 5 plus x cubed over x plus 2. Now notice that we have problem at the top. It's not in descending order. It is not in descending order. So redo it first. Reorder it. So that will be x cubed minus 3x squared plus 5. I'm sorry, plus x plus 5. And at the bottom, we will have x plus 2. Okay, so reorder that first. Reorder. Now then, we will do the long division. Let me do it on the right hand side here. Good thing that we don't need to use any placeholder. We just go on. Now let me give you 2 or 3 minutes to work on this problem. Okay, please do so. I will stop the recording. X go to x cubed, x squared times. So this will be x cubed plus 2x squared. When I subtract, negative 3 minus 2, that's negative 5. So this is negative 5x squared plus x. Now x goes to negative 5x squared minus 5x times. So I get negative 5x squared minus 10x, which when I subtract, I get 1 minus negative 10, that's 11. So this is 11x plus 5. X times 11 gives us 11x. Then I get 11x plus 22. When I subtract this, 5 minus 22 is negative 17. Okay, so the quotient is therefore x squared minus 5x plus 11 minus 17 over x plus 2. Okay, that's the long division. To help you dissect the procedure later on, I would like you to do the long division problems. Long division. From section 3.2 That's suggested homework. 3.2, number 1, number 3, and then yeah, that's for now, 2 questions. Actually, you can do number 7 too, but this number 7, it may be too easy such that you get confused. Okay, now how about synthetic division? The synthetic division. Now, synthetic division can only be used when we divide a polynomial by a binomial x minus c4. So it's either x plus 2, x minus 5, x plus or minus something. But it has to be x plus or minus something. Cannot have 2x or 3x or 5x. No, no, no. It has to be x plus minus something. Okay? So basically, if you have a polynomial px divided by x minus c. So our last example actually okay with that. So let me use that as an example. Copy. Suppose we have this now. Of course, we still need to make it into descending order. So this is x cubed minus 3x squared plus x plus 5 divided by x plus 2. Now that x plus 2, it's basically, this is the same to say x minus negative 2. Okay, x minus negative 2. Now, how to do the synthetic division? Synthetic division becomes very efficient because what we will do is we basically ignore all the variables first. Now, the way we do synthetic division will be as the following. There will be 3 lines. There will be 3 rows. The first row here in descending order, the first row inside the box is the coefficients of the numerator. In descending order, 1, negative 3, 1, 5. And of course, don't forget if you need a placeholder also. Okay, now that's what you have in the first row. The second row in the outside, you will put the C. Okay, so because you divide by x plus 2, the C will be negative 2. Now then, how about the procedure? The procedure will be as the following. The first number here will always be copied down underneath here. Whatever you have there, that's what you copy down. Boom. Okay, always, just copy that down. Now then, we will do the following work. 1 times -2, put that number there. 1 times -2 is -2. And then you add this. And then you add this column, you get -5. Now we repeat the procedure again. -5 times -2 is +10. And then we add. And then do the same thing again. So 11 times -2 is -22. And then you add, you get -17. Okay. Now this part here is the coefficient for the quotient. And we call this the remainder. This is the remainder. Now, the degree here is degree of 3, the power of 3. Now, once you divide by x plus something or x minus something, then the degree here will be 1 less. Degree of 2. Now, that 1 corresponds to the degree of 2, right? So that will be 1x squared. And then you use the descending order again. X squared minus 5x plus 11 minus 7 over x plus 2. And I believe this will give us the same result we have up here. Okay, the same result with this. Right, you see that? Now, synthetic division becomes a lot more efficient compared to long division because of that you basically put them in order and you don't need to write the variable x, that's one. And second, instead of subtracting, we actually do addition. Okay, instead of subtracting, we add because the subtraction already being incorporated into the opposite there. So instead of dividing by x plus 2, you divide by quote unquote -2. Okay, now let's do one example. Let me pick it from the book. And this kind of like polynomial can be done actually very, very fast. Extremely fast. So let's say I do number 30. Number 30, -2x to the 4th plus 10x minus 3 big over x minus 3. Now the synthetic division, the way I write my synthetic division is slightly different from the way our textbook write it. Okay, the way I write it here is actually very close, basically the way I learned it how many years ago. Okay, but the textbook type it differently because of the typesetting. It's easier to type it the way they type it instead of writing it the way I write right now. But I still follow my old way. This is degree of 4. This is degree of 4. Okay, so the degree of 3 is 0. Degree of 2 is 0. The degree of 1 is 10. The constant is -3. And I will divide by x minus 3. So the c is positive. Okay, so this is x minus c, right? So the C is 3. Okay. Now, I hope I can write less, but still complete enough. Now the first number goes down, -2, and then multiply -6. You add, multiply, -18. You add, multiply, -54. You add, multiply, this is -100, 152. So this is -155. Do I count it wrong? Four, 4, 3, 2, 1 constant. Yeah, that's right. Ah, now I see. I make a mistake here. This should be -44. So -44 times 3, that's -132. -132, so this is -135. Then the quotient here is -2x cubed, 1 degree less. And then you follow the next term, 1 degree less, the next term, 1 degree less, the next term, 1 degree less, minus 135 over x minus 3. Now, for you to be successful, in this 3.1, 3.2, 3.3, 3.4, I wonder if I cover 3.4. I will do a little bit. Yeah. The next 4 sections, 3.1, 2, 3, 4, and also 3.5, for you to be successful in this chapter, you need to be very, very fluent with synthetic division. I write it down. You need to be able to perform synthetic division fast. To be successful in this chapter. This is one of the basic ingredients. Now the thing is, it's so important because a lot of material in this section relies on how good you are in doing synthetic division. Okay, so when you do your synthetic division later on, it should be something automatic. You should not like, how to do this again? What should I write here? What should I write there? Like that. No. You should know what to do already. Okay, now let me ask you to do one problem, including your break. Okay, let me ask you to do number 28. Number 28, the question is, 5x cubed minus 18x squared minus 15 divided by x minus 4. Okay, and then so we come back at 115. Now, once we get to 115, things will go quite fast. Not because I want to make it fast, no, not because I want to make it fast, but because it's a lot of the synthetic division will be 5, negative 18. That's degree of 2, degree of 0, degree of 1, degree of 0, and then the C is 4. So this is 5, 22, 8, 8, 32. So this is 17. So the quotient is 5x squared plus 2x plus 8 plus 17 over x minus 4. Okay, now that's about the division. Now from here, I want to go on to 3.2 first. Now you will see the discussion from now, a lot of them being theoretical, but then we can apply that right away. Now in 3.2, this 3.2, we first learn division, which we did earlier. Division, long division, and synthetic division. Like what I said earlier, synthetic division is something you should be very good at by tomorrow. By tomorrow, you should be very good at already. Okay, this is done earlier. This is done earlier. Okay, now then part B, the second part of 3.2 that I purposely separate the division because it's so important. It requires its separate attention. Okay, now the second is remainder theorem. Remainder theorem. The third part is factor theorem. Okay, what is remainder theorem? Part B, remainder theorem. It says the following. If Px is divided by x minus c, then the remainder let's call that R, the remainder R is equals to Px. Okay, I use Px instead of a regular function. I purposely use the notation Px for polynomial. So if a polynomial divided by x minus c, I'm sorry, so the remainder is Pc, not Px, is Pc. If Px, a polynomial divided by x minus c, then the remainder R is equals to Pc. Okay, let's do this example here. Let's do this example here. Suppose I have x cubed minus 2x plus 5 over x plus 3. Okay, so this will be my Px, right? This is my Px. And my C is negative 3. Okay, now let's do the synthetic division. If I do the synthetic division, 1, 0, negative 2, 5, right? Degree of 3, degree of 2, degree of 1, degree of 0. And this is negative 3 outside. 1, negative 3, negative 3, 9, 7, -21. This is -16. Now, that's the remainder, right? This is the remainder. Now, what this remainder theorem says is that when you plug in P -3 into that Px, if you plug that in, you will get that -16. Okay, the remainder is the same to that P -3. Okay, that's what it says. Now, with that said, then the consequence of it is the following. With that said, if Px equals to x cubed minus 2x plus 5, and we want to find P -3, we can use syntactic division and find its remainder. Okay, that's the idea. That's the idea. You need to exercise with the. You can do exercise later on at home. Okay, to confirm this. You don't need to do a lot. Okay, you don't need to do a lot. Just do some problems to actually internalize the idea. Okay. But I hope you also see that in between, if you don't know how to do syntactic division, then you will get slowed down by too much. Because if you cannot do syntactic division, you have to do long division. But when you do long division, it will take you too long. Okay, so you don't have any way out. You have to know how to do syntactic division fast. Okay, now the proof for that theorem. Let Px be a polynomial divided by x minus c give the quotient Qx with remainder r. So basically Px, when you divide it by x minus c, we get the quotient Qx plus remainder r over x minus c. If I use the example we have up here, x cubed minus 2x plus 5 over x plus 3 equals to x squared minus 3x plus 7. That's the quotient, minus, maybe I use plus 16, negative 16 over x plus 3. Okay. That's from our last example, right? That's what it looks like. Now, go back to my proof. Okay, so if we divide by x minus c, we get the quotient and remainder. So that's what we're supposed to look like. It's supposed to look like. Now multiply by the LCD. Multiply by x minus c. Multiply by x minus c. Then we will get the polynomial equals to x minus c of qx plus r. Now, the thing is, if we replace x by c, if we replace x by c, then I will get pc equals to c minus c times qc plus r. However, this guy is equal to 0. So the whole term here will be 0. Right? Let me write it down explicitly. So PC equals to 0 times QC plus R, but 0 times anything will be just 0. Therefore, when you plug C into the polynomial, that's equals to the remainder. Now the thing is, we can find the remainder quite fast using syntactic division. Right? We can find the remainder quite fast using syntactic division. Okay, so that's how we will be able to use the remainder as the value of the polynomial at C. Borrowing the example we have earlier, this is x cubed minus 2x plus 5 equals to x plus 3, x squared minus 3x plus 7 minus 16. When I replace my x by negative 3, now this will be 0 here, whatever here, minus 16. So the expression we have on the left-hand side, if you plug negative 3 into the polynomial, that's the same to remainder of the polynomial divided by x minus c, divided by x plus 3. Okay, so that's the remainder theorem. Okay, that's the remainder theorem. So to find the value of the polynomial at certain number, in this case negative 3, okay, I can use syntactic division and find the remainder. I divide that polynomial by x plus 3. Okay, so instead of plugging negative 3 into the polynomial, right, syntactic division will be much faster if you know how to do it fast. Otherwise, of course, if Thomas, what happens if I cannot do it fast? Then if you cannot do polynomial syntactic division fast, I don't think you can do anything fast enough. Yeah. It does take some practice though, but if you already tell you since the beginning that I cannot do it fast, Thomas, then you basically set yourself to be a slow person. You tell yourself you cannot do fast. Okay, you kind of like, or try to enforce instead of like try to change. You try to enforce and do not want to change. No. Practice. Okay, practice makes perfect. Practice at least make you faster. Okay. Now, I go on. The consequence of syntactic division, consequence of remainder theorem is factor theorem. Now, what is factor theorem? Factor theorem says the following. If PC equals to 0, then x minus c is a factor of px. The proof. From that remainder theorem, we see the following, that px equals to x minus c times qx plus r. Right? Now, what happens if r is 0? If r, which is pc, is equals to 0, then px equals to x minus c times qx. And by definition, then qx, i.e. x minus c, is a factor of px. Now, let me do problems to reflect this situation here. For example, I pick question number 18. Okay, let fx equals to x to the 4th minus 3x cubed plus 5x minus 2. Show that c equals to 2 is a factor. Show that x minus 2 is a factor. X minus 2 is a factor of fx. Okay, solution. The idea is x minus 2 is a factor of fx if f2 equals to 0. Okay, just to bring you up to some definition that we did before, this is basically means 2 is a 0 of fx, but I will say that more explicitly later on. Yeah, x minus 2 is a factor of fx if 2 is a 0 of fx. Okay, so what I need to do is, we need to show f2 equals to 0. Now, how do we show that? Now, you can plug that in, but I believe syntactic division is faster. Okay, so 1, -3, 0, 5, -2 divided by x minus 2. Okay, so here, basically by remainder theorem, remainder theorem. The remainder is 0, right? Okay, the remainder is 0. Therefore, F2 is also equals to 0. And then by factor theorem, because x minus 2 is a factor when the remainder is 0. Okay, so x minus 2 is a factor of fx. Now, basically, I want you to realize that we already have this trinity here. What trinity? Let px be a polynomial. Now, then C is a 0 of px. By definition, it means pc equals 0. That is by definition. Now, according to factor theorem, according to remainder theorem, if PC equals to 0, means the remainder equals to 0. That's the remainder theorem. That's what the remainder theorem say. If the remainder is 0, then PC also equals to 0. Now, according to factor theorem, if the remainder is 0 or PC equals to 0, then x minus c is a factor of px. Okay, this is by factor theorem. Maybe I erase this. So what happened then? You will have these four things here come together. Now I want you to realize that how do we use this later? If C is a real number, then C comma 0 is an x-intercept of the graph of Px, which is our main goal, to graph a function. So the long story later on is, if I give you a polynomial, how do you graph them? You need to find the y-intercept, which is easy. To find x-intercept, then you need to do a lot of theorems. Put together becomes like this. Okay, so keep in mind that the remainder is the same to PC. Okay, so if the remainder is 0, means PC equals to 0. If PC equals to 0, then C is a 0. It means x minus c is a factor of px. And if c is a real number, then c comma 0 is an x-intercept. Okay. Ooh, that's a lot to put together. Okay, that's a lot to put together. Okay, let me jump to kind of like get into what they do in 3.1. So in 3.1, we will do the following. Let me ask you to do this first. Try number 32 in section 3.2. The question is, oh, I'm sorry, not this one, my bad. No, not this one, not this one. Did we do number 14? Yeah, no, not yet, number 14. So section 3.2, I would like you to try number 14. Would you like 14 or 42? Maybe number 42 then, number 42. So it seems to be hard, a bit harder, but it's actually not. Okay, so let fx equals to 4x cubed minus 9x squared minus 8x minus 3. And the question is, show that 3x equals to 3 is a 0. I think that's something you can do. Okay, I think that's something you can do. So the solution is, this question is easy, I believe. So how do we do this? I use synthetic division. Thomas, can I just plug in 3 into the function? Okay. Yes, you can. To answer this question, yes. Yes, you can. Okay. So F3 equals to 4 times 3 cubed minus 9 times 3 squared minus 8 times 3 minus 3. This is 4 times 27 minus 9 times 9 minus 8 times 3 minus 3. This is 108 minus 81 minus 24 minus 3. You will see that's equals to 0. So Thomas, yes, x equals to 3 is a 0. So x equals 3 by the definition is 0 of fx. See, Thomas, I answered the question. Okay, but you cannot answer the follow-up question. We won't be able to answer the follow-up question from there. Graph the function. That's the follow-up question. What you get here is only this. Well, 3 is a real number, so 3, 0 is an x-intercept. That's the most you can say. But with me, I give you a 0, and I expect you to be able to go on from there to find the rest of the zeros. Therefore, you get the rest of x-intercepts. Therefore, you can graph it. Strange, huh? That only one little information. As if I'm telling you this. I give you this function, and then I ask you, graph this function, and to make your life easier, I tell you in advance that 3 is a 0. And how can you use that? How can you use that 3 to move forward a lot more? Okay. Now the secret is the following. Okay, then I divide by x minus 3, right? So 12. This is 3. This is 9. This is 1. This is 3. This is negative 3. This is 0. Okay. So yes, at this point, by remainder theorem, my remainder theorem, is a 0 of fx. Okay, but then how do I use that information that 3 is a 0 of fx to go on and to go on further, to graph it. Because 3 is a 0 of fx, then by factor theorem, x minus 3 is a factor of fx. In fact, now I can say fx equals to x minus 3 times 4x squared plus 3x plus 1. Okay. Now then later on, what you can do is you can try to factor this further. It's degree of 2 already. Either you factor it or find the x-intercepts from there. Okay, so the plan is this. I use that 1 0. I use this 0 here. The term is 0. Okay, knowing that it is a 0, implicitly we also know that it is a factor. Now, once it is a factor, then I can get the quotient, right? I can get the quotient, and then later on we can go on from here. Okay, now I will go back to 3.1. I know I only have like around 10 minutes left. I go back to 3.1. I may do only one problem. I may do only one problem. Tomorrow I will continue on the 3.1 again, but I plan to do only one problem here to give you a very good feeling about how do we actually graph things. Suppose, for example, give me a second. Give me a second. Okay, so we do the following. Let Px be, x to the 4th minus 3x cubed minus 8x squared plus 12x plus 16. And how do we use this though? And 2 and negative 2 are zeros of Px. Now use these informations to graph Px. Okay, and now what I want to show you is this. Basically, if you have enough zeros, then you can factor the polynomial. Once the polynomial is being factored, then you can graph it. Okay, now then tomorrow we will then focus more on how to get this 2 and negative 2. So right now, that's something given to us. Tomorrow, we'll see the situation where we don't have any hint but just the polynomial. Okay, now so solution. Now knowing 2 is a 0 means 2 and negative 2 are zeros of Px implies x minus 2 and x plus 2 are factors of px. Okay, so let's see. That's 1, -3, -8, 12, 16 divided by x minus 2. We expect that the bottom right will be 0 here. That's what we expect because we know 2 is a 0, right? So 1, 2, -1, -2, -10, -20. This is -8, -16, 0. Now the nice thing about this is, then I can continue from that last row, 1, -1, -10, -8, and go further because -2 is also a 0. Okay, so I reduce that even further. 1, -2, -3, this is 6, -4, 8, 0. What does it mean? It means that Px, which is x to the 4th minus 3x cubed minus 8x squared plus 12x plus 16. Because of this, I get x minus 2 times x cubed minus x squared minus 10x minus 8. And going further, because x minus 2 is a 0, means x plus 2 is a factor. And then I get x squared minus 3x minus 4. Now, once it is quadratic, we can compute this, we can factor this also further. Okay, so this is x minus 2, x plus 2, x minus 4, x plus 1. That's what our Px is. Then from there we know that the x-intercepts, let's say the zeros first. The zeros, using those two zeros, I get the rest of the zeros. The zeros are 2, -2, that's given, right? But using those two zeros, I reduce the polynomial down to the degree of 2, and then I can factor it. Now I get the rest of the zeros. Therefore, the x-intercepts are 2, 0, -2, 0, 4, 0, -1, 0. The technique I show you here, you don't see that in our book, at least not explicitly. Our textbook tried to explain too many things at once in 3.1. What I try to do is to connect what we learned just now, remainder theorem, syntactic division, and then go to remainder theorem, and go to factor theorem. Now I get the x-intercepts, and then I try to relate to something else, the sign graph that we learned in 1 point something. Okay, sign graph for Px. We have the zeros are -2, -1, 2, and 4. Those are the zeros. And then the y-intercept, is 0, 16, right? That's the y-intercept. Which is positive. And each of these zeros has multiplicity of 1. Exponent 1, exponent 1. I wonder if you remember that. The exponent are all 1 because the exponent is is odd, then every time it jumps across the critical numbers, it changes signs. Now, knowing the plus minus tell us that the graph is above or below the x-axis. Okay, now let me sketch the graph approximately. This is just approximation. This is just approximation. So my y-intercept is 0, 16. My x-intercepts are -1, -2, 2, and then 4. Between -2 and 1, it's negative. So it must be below x-axis. Between -1 and 2 is positive, which means it must be above x-axis. From 2 to 4, it's negative, so it must be below x-axis. Now, from 4 to infinity is positive, then it will go to positive infinity here. And to the left of -2 is also positive, so it goes to positive infinity there. So that's what the graph looks like. Okay, now the thing is, in calculus later on, then you will learn to find, in calculus, not here, you will learn to find what coordinates this, what coordinate is this, and where's the peak here. But in pre-calculus, we just ignore it for now. Okay, we just use the x-intercept and y-intercept and something called far end behavior. Okay, something called far end behavior. This is where I will stop for now. This is where I will stop for now. From this 3.1, I call that 3.1a. I would like you to try to do number 19, number 21. It relies on factoring, but I believe the factoring is quite easy to do. Number 25. And then number 27 and 29. Yeah, we are not done yet with this section. We are not done yet with this section. But what we will do tomorrow is actually on the easy side already. Okay? Yeah, what we'll do tomorrow will be on the easy side already. Now, in overall, we will learn this. Overall, we will learn in 3.1 and 3 up to 3.4, we will learn the following. The one we have learned, division. Either long division, synthetic division. And we have also learned remainder theorem. Factor theorem, that's quite short, but very useful. Okay, now then what we will do tomorrow, I will first quote fundamental theorem of algebra. Fundamental theorem of algebra. And then intermediate value theorem. And then far ends behavior. And then rational zero theorems. You know what? I will do Let's cut the rule of sign first. Of sign, and then rational zero theorem. Conjugate theorem, conjugate zero theorem, I may quote a little bit boundedness theorem. But all of these actually being used to do only one thing, to find the zeros of Px when the degree is higher than 2. When the degree of 2 is quadratic, so you can just use formula. But if degree is 3, degree of 4, 5, even 6, then we need to do some guessing game already, and we need to combine all we know about these theorems to actually zoom into the actual zeros. None of these theorems can give us the precise zeros, but the combination of these tools enable us to find out those zeros. Okay, that's for today. See you tomorrow. Make sure you do your suggested homework.